Good morning and welcome to Versailles. We look forward to being together here for 2 days of discussion from units to the universe, future revolutions in metrology. I'd like to hand over to the President of the CIPM, Dr. Wynand Louw, who will come and make some introductory remarks for us. Wynand.
Good morning, everyone. Bonjour. It's such a pleasure to be here today. You know, yesterday at UNESCO, those of you that were there, that was the celebration of the signing of the Meter Convention, so the diplomatic part of our convention of the BIPM, the establishment of the BIPM. But now, today, is actually, guess what? The first day of the next 50 years. And we are here to really enjoy it. We are here to stand on the shoulders of everyone before us, all the scientific achievements. But from this point onwards, the future of the BIPM is in our hands. And I really want to invite you to enjoy these 2 days with us. Take off your ties. It's the last time you will see me with a tie today. And we're just going to enjoy it. So the conference has 5 sessions based on the topics of our CIPM strategy, and I'm quite sure by now all of you have seen the strategy, and basically just saying that we need to be more cross-cutting, and we're putting everything in place for our community to work together without boundaries between the consultative committees to form joint task groups and forums, and many of you are already participating in that. But so the first 5 sessions are basically reflecting on that. And the 6th session is very exciting because it's forward-looking. It's a session forward-looking on metrology in space. And I'm quite sure all of you are very interested to see that. So our idea as the CIPM was to bring in excellent scientists from outside our metrology community as well, to hear to the conference and to hear what challenges they see for accurate measurement in the next decades. We want active discussions, so we will have panel discussions, but I think those of you that were there yesterday, today is vibrant. We are expecting questions from the floor, and we really hope that you will help us to make it a great success. So as we are talking about the future, in line with our CIPM 2030 plus strategy, the CIPM called for posters in 9 different areas mentioned in our strategy. So we selected 9 of them, and they will be presented this afternoon, or basically after the sessions. And we also invited especially young scientists to submit their ideas on posters. And there's also one from them that will also be presented. So I think it's really our opportunity to showcase the young talent, the young scientists, the new energy in our organization this afternoon. So this conference is for our community and our collaborators to come together and discuss the future of metrology. Let's make the next 50 years great. Thank you.
Good morning, ladies and gentlemen. It's a great pleasure for me to open this first session of this conference on the very important topic of metrology in the quantum era. This week we are celebrating the 150th anniversary of the signing of the Meter Convention, but this year we are also recognizing that it is 100 years since the initial formulation of quantum mechanics. In this session we'll have 2 presentations which will be followed by a panel discussion with experts on quantum metrology. The first presentation will be on quantum, the entangled tale of metrology and technology. It will be given by Barbara Goldstein from the National Institute of Standards and Technology of the United States. Barbara serves as Associate director of the NIST Physical Measurement Laboratory. She leads the NIST on the CHIP program, which is developing a suite of quantum sensors and standards to take precision measurements out of the lab and into the field. She's a leader in international quantum standardization and is co-leading the launch of a new international collaboration referred to as NMI-Q to foster collaboration among the world's metrology institutes to advance the quantum economy. She served as inaugural chair of 𝐒𝐞𝐽 Technical Committee 25, Quantum Measurement and Quantum Information, and is now president-elect of 𝐒𝐞𝐽. Barbara, please.
Green go. Okay, thank you so much for that very kind introduction, and it's an honor of a lifetime, really, to be up on this podium, to share this podium with all the other honored speakers from yesterday and for the next 2 days. So thank you for inviting me and helping me help you celebrate the birthday of the BIPM. So in this talk, I'm going to start out by just talking about what's so cool about quantum, and then I'm going to delve into the symbiotic relationship between quantum technology and quantum metrology, and then I'll end with some comments on the evolving role of the National Metrology Institute. So first of all, emerging technologies demand innovations in metrology. So in areas like quantum, it's very important that we stay agile because the technology landscape is changing so rapidly. And sometimes it's important to just be able to make any measurement at all. And if traceability is needed or when it's needed, that may lag. It's important to be for folks to be able to compare apples to oranges in this quickly evolving landscape. And we may not have time to wait for standards to be mature because things may change before that happens. But it's also true that advances in metrology also demand advances in technology. So different technologies that are emerging on the landscape now are offering different benefits to metrology. So quantum is giving us opportunities for higher precision, pulling faint signals out of the noise, and for more stable standards. But other technologies are also quite important. Integrated photonics and nanofabrication advances are helping us miniaturize standards and sensors. Digitalization is letting us track the provenance of our standards and their calibrations and to notice when calibrations expire. You know, I'm so short, I have to kind of look like this over my the podium. Anyway, maybe I'll just stand over here and not trip. But digital twins and sensor networks offer us, I think, also opportunities for how do we deal with the complexity of traceability in this changing metrological landscape. And then we might turn to artificial intelligence to manage what's currently intractable and to look for patterns of drift. So the rest of this talk, I'm going to zero in on quantum. And I'm going to share my view of what's so cool about it. So first of all, energy is quantized. So if you have a cesium atom, you can pretty much count on the transition levels within that atom, and we can use nature's reference like that to create better sensors. Matter acts like both waves and particles, and we can use this trick of quantum mechanics to have innovative and new ways of imaging. Observing a system changes it. So if you've got an eavesdropper on the line, you'll notice because it's going to change the signal. And uncertainty, as uncomfortable as we may be with that, it's a fundamental part of nature. We can't try to wish it away or engineer it away, but we can work with it. And we can squeeze it out of the things that we care most about measuring, so the things that we can squeeze it out of the things that we're not interested. We can squeeze it away, is what I'm trying to say, so that the things we care most about measuring, we can get higher precision on and push all that uncertainty into the stuff that's not so important. Matter can be entangled, and we can use this to teleport information. And I have to say that at least one renowned quantum theorist has told me we ought to be able to teleport people. I know that we're not used to Star Trek, but that's because people are basically, we're a collection of information, so the jury's out on that one. But, and matter can be in a superposition of states, so it could be on, off, or both at the same time, and we can take advantage of this little trick to make qubits rather than bits of information so that we can tackle more complex computational problems. So I have to say I have coin envy because for the last hour we've been staring at this beautiful flipping coin that shows the reflection and everything. So you'll have to put up with my hopefully substance over style on my particular coins. So there's a flip side of this coin, right? We use quantum to do better metrology. Metrology institutes like NIST were the first to develop quantum devices because we needed these tricks of quantum mechanics to make better measurements. So in a way, we've been the first to be the beneficiaries of this new wave of quantum technology. And we've used that to do things like use Josephson junctions to make standard volt and ion traps to make better clocks. But there is the flip side of the coin, which doesn't spin half as nicely, but I'm going to work on that. So what does industry need from us, metrologists, to make better quantum technologies? So they still need Josephson junctions for standard volt, but that same technology can be used to make superconducting qubits for computers. And they still need ion traps to make better clocks. But that same technology can be used for another platform for quantum computing. And these technologies need entirely new ways to measure and characterize. So quantum form metrology, what does it offer? We heard a fair amount about this yesterday, but here's a little laundry list. The promise of quantum standards, right? They can be inherently stable. And so again, like I was saying, we can take advantage, for example, of the energy transitions within an atom. And then you can combine that with the redefinition of the SI, and now we're democratizing metrology. So anybody with a very sophisticated garage that thinks they can get to Planck's constant can now create their own, realize their own primary standards. They offer higher precision. So like I was saying, we can squeeze the uncertainty out of what we care about, but we can also look at entangling sensors to cancel the noise across them and beat the standard quantum limit. And you put all this together, we can have metrology on the move. And that's what NIST on a chip is about, and I'm going to talk to you about that in just a minute. And it's particularly relevant for the very small and the very faint. And we have folks at NIST, Sergei Polyakov, who's pulling out the signal of a single targeted biomolecule in very, very large ensembles. And we can look towards innovative applications like NV centers that can be tucked inside of living systems and provide a signal. So atoms are intrinsic standards, so when we want to make a clock, we have to control that environment very, very well because those transition levels can shift based on the environment. So our pristine labs are excellent places to have great clocks, but if we let the environment vary, suddenly we can turn that clock into a sensor. So the sensitivity to the environment, really bad for clocks, really good for sensors. And now, as I was saying, NIST on a chip is all about making metrology mobile. So the overall vision of the NIST on a Chip program is to take devices that look like this. Strontium atomic clock takes up full optical tables, requires highly educated people to operate it. This 100 kilowatt thermal power meter that is so big it has to be carted around in a van in order to get to where you need to make the measurement. Or this horn antenna that requires specialized facilities just in order to operate. Oops, sorry. And to shrink them down to devices that look like this, an atomic clock the size of a grain of rice, a power meter small enough to embed in an additive manufacturing machine or other equipment that needs it, or vapor cells of atoms that can be used as exquisite sensors. And the big vision of NIST on a Chip is that we ought to be able to bundle those capabilities together into a single package and have those be cheap, easy to manufacture, easy to deploy, easy to embed, and put into environments where they never are needed to be pulled back from. So you could bundle them together and send them up in rockets, which we've done with our radiometers, for example, and never worry about them coming back for calibration because they're intrinsically accurate, or they tell you when they're no longer working. So I know I keep talking about us shrinking our technology down, but we're not just making things smaller, we're actually measuring things in very different ways, and again, this is where quantum helps us out. So we measure temperature now by looking at changes in the optical properties of materials. We can measure distance by looking at wavelengths within atoms, or we can measure power by measuring the slight force that that light exerts on matter. So I always like to point to the chip scale atomic clock as sort of a poster child for the overall program. So John Kitching had the audacious idea that you could actually take that very complicated apparatus and shrink it down to the size of a grain of rice. And we couldn't do it on our own at NIST. We had to have help. So we had significant DARPA funding that funded not just us. NIST got about 10% of that funding. The rest went out to industry partners and other partners. But at the end of the day, we were wildly successful, and now there's, you can buy this product off the shelf. And that's what we want to do across the board for all the things that we currently measure in-house. And we're also working on other types of chip scale clocks, like this beam clock, and then next generation optical chip scale clocks. So that's a little bit about how quantum is helping metrology, but now, what is it going to take to spur a quantum industry? What does the industry need from us? So first, they need us to continue to make research innovations so they can take our good ideas and turn them into products. Honeywell did this, for example. They scooped up decades of public domain ion trap research coming out of Boulder. So we created this first surface ion trap in 2005, but they did something we could never do. They hired 100 people, invested like $100 million, stood up a new company and spun it off as Quantinuum. So industry still looks to us for those innovations, but they also look to us for innovations in metrology. So quantum computing companies have talked to me about wanting to embed metrology right on the chip with the ion traps. And of course, a lot of these devices work at cryogenic temperatures, so we need to get more skilled at the temperature, not just within a cryostat, but in different locations within a cryostat. I'm sure we'll hear more about that in the following talk that's going to do a deeper technical dive. We are standing up new calibration services, for example, for single photon detectors. And the picture on the bottom shows a fiber coupling technique in order to pull signals out of a cryostat that NIST developed, and it became ubiquitous within the industry. And here's where I'd give a nod to Wynand, who's one of our key researchers that we lost recently. And then they look to us to help with standards and pre-standardization work, and I'm going to talk a little more about that as well. So this picture is my take on the technology life cycle. So I promised Michael that this was not going to be a standards talk. So, but forgive me because I just couldn't help myself. So anyway, standards. So I know when we say standards in this room, we think of physical standards, but there are also documentary standards very important to help spur an industry along. So you can think of the life cycle as going from invention to de-risking technology through things like prototyping, developing use cases to ensure that you have a market, turning those innovations into product through engineering and scaling. Then once they're products, you need to maintain those products and boost consumer confidence. And then at the end of the day, these products are out in the field. You want to learn from the experience from the field so that you can then feed into the next generation of that product. And standards support every step of that process. So I always say it's never too early to develop terminology standards. First, it's just a great community building exercise to level set even among researchers, but terminology standards also help bridge the gap between different communities, like the research community and the commercial community. But then when you're in the phase of de-risking technology to get it closer to market, characterization and performance is highly important because you need to be able to measure accurately what you're developing to know if you're on the right path. Metrics and benchmarks. I've been involved in the Quantum Economic Development Consortium Standards Group since the very first meeting, and at the very first meeting, this was what they talked about. And this has been the longest running project, I believe, in the QEDC, because end users want to be able to sort the hype out from the truth, and they want to be able to compare apples and oranges. And then once we have products on the market, interface and interoperability standards become highly prevalent because you want companies to be able to innovate on what they know best and know that should they wildly succeed at the products they're creating, it's going to fit into a larger ecosystem. They don't have to worry about what they're fitting into because that standard is there to guide the entire landscape. And then certification standards can help users gain confidence in the products that they're purchasing. And then finally, we need standards to funnel that information from the experience in the field down to the manufacturers and designers of the next generation products. So that's standards, but what do standards need to be successful? Well, they need good, solid pre-standardization work because the best standards are science-based but industry-driven. So to help that process along, I'm working together with several colleagues in the room, some that you'll hear from today, to stand up a new organization that we're calling NMIQ. And the purpose of NMIQ is to leverage the power that metrology institutes have, not just the power, that's probably the wrong word, but it's our deep expertise, our neutrality, our objectivity, our deep connections with industry, to develop best measurement practices so that when these technologies are brought up for standardization, they have ground truth to draw on so that those standards have that good, solid science basis. And we'll work with industry to make sure that what we're talking about also fills industry gaps. So as you can see here, we've got several people here. JT is our CIPM rep. Tim Pryor, Nicholas Bethman, Davide Calanico from Italy are all helping in this grand adventure. And we held a meeting at the BIPM last March to get this idea going, to make sure we were on the right track, to make sure we had community support. And we had 149 participants from 43 different NMIs from 39 different countries. And at the end of the day, everyone agreed that, yes, indeed, we need to do this pre-standardization work for the betterment of the entire community. And I encourage you to look at this workshop report. We wrote a very thorough report, and we've included all the presentations. So before the workshop, we ran a survey just to see where NMI stood. It turned out that only about 60% of our metrology institutes that were participating had programs in quantum, so it's not ubiquitous. And then we have, these are just a sampling of some of the questions we asked about what areas of quantum you care most about. And you can see that clocks, of course, enjoy a lot of popularity and a lot of activity. And then there's areas like Majorana qubits that it's not zero, but pretty darn close. And that there's a lot of interest in areas where people don't yet have activity. And that engagement with the quantum industry is taking metrology institutes beyond their usual core functions. So, and to sort of complement this, to look at both sides of the coin here, the CIPM and the BIPM, so JT is championing this new work group on the quantum for metrology side, which is the natural, so BIPM is the natural place to really coordinate those kinds of activities, and I guess that's part of what Martin was referring to as more cross-cut activity. And then NMIQ will focus in on what metrology do we need for the quantum industry. And I want to give a little shout out here to 𝐼𝐞𝐲. So as was mentioned in my introduction, I've been the inaugural chair of the Quantum Measurement and Quantum Information Group that I'm gladly turning over to my colleague Nicholas Bettman as of just a few days ago. So thank you, Nicholas. But one of the activities that we've kicked off within that group is a book that we're calling Metrology in the Quantum Era, where we're inviting contributions in both of these topics. So we have a series of contributors lined up, but if somebody wants to jump in, please let us know. So what this all comes down to is that metrology institutes are being asked to do more than they've maybe been used to doing in the past. So first of all, there's the traceability challenge, right? In a world where measurement standards might be inspired by research that we're doing within a metrology institute, but not developed within that metrology institute and not used only within our pristine labs, what does traceability mean? And if we're not calibrating these standards, how can you have this unbroken chain back to a metrology institute? And what does intrinsic really mean? Just because it's quantum doesn't mean it's irreproachable. And as my colleague in the Air Force likes to say, okay, I'm going to take one of your force sensors, I'm going to put it on an aircraft carrier, then I'm going to land my plane on it. You tell me, is it going to work? So, you know, there's a lot of practical things we still have to worry about. And then what's the role of the mutual recognition agreement? What are we recognizing when the standards are made by third parties? And we're not producing them. So a case study is the Josephson voltage standard. This has become rather ubiquitous as a primary realization of the volt, so it certainly fits nicely within the definition of an intrinsic standard. And it's not calibrated because it's a realization, right? But how do we know it's still working? So what we do is we verify them with round robins that get conducted about every 2 or 3 years. But so it's already complicated for something that we're still producing within our NMIs. And oh, by the way, this is a NIST on a chip device, but it doesn't exactly check my cheap box, you know, so for $250,000, you could have one too. But anyway, we make them, and I think even that price tag, right, makes us know where they are and where they're operating, so we have a lot of information on them and on the environments that they operate in. But what about all these other devices, our temperature sensors that could be very cheap and very ubiquitous, the size of a human hair or whatever? How can we provide assurance for things like that we aren't even manufacturing and we don't know where they are? So some strategies, potentially for dealing with this. We could impose a quality system on these third-party manufacturers. Thank you. Do they need to qualify their manufacturing processes? Do they need to participate in regular round robins with us? And how do we handle innovations that they layer on top of the designs that we're creating within an NMI? And how can manufacturers anticipate all the environments within where their devices will be used? Do you impose quality assurance measures on the users? Do they have to participate? Do we have to make these chip scale standards somehow report back to some metrology mothership? And I can tell you the DoD is not interested in that. Do you need to run traditional check calibrations, like have maybe more traditionally calibrated mass sets to check on your kibble balances? And how can we leverage things like AI digital twins and sensor networks to deal with the traceability problem? For example, a digital twin, you could have a twin of a device in your own lab. The device is out in the wild somewhere. You take your best guess at the environment that it's in, and then you can monitor the twin to see if you think the device itself is still working. These are all just ideas at this point. And then finally, metrology institutes are expanding the role that we play, right? NMIs are doing things like establishing consortia, like NIST did with the Quantum Economic Development Consortia. They're launching incubators, which I believe PTB has done. We're all contributing to the national strategies in our country. We're establishing test beds. We're leading, seeding, and contributing to standards. So I know, again, PTB is leading the Mirror Committee, as is NIST is administering our Mirror Committee to this international joint technical committee that's focusing on quantum standards. Collaborative research with industry and academia, that's not necessarily new, but for instance, MPL has very robust program in that area, and I was just hearing about LNE's new program to look at quantum computing components. And then we're asked to do proof of principle novel measurements for things that we've never had to measure before. And so with that, I thank you for your attention.
Barbara, thank you very much for this very interesting overview talk on the mutual benefits from progress in quantum physics, metrology, quantum technologies, and the potential impact on the role of the NMIs. If this presentation raised any questions, please keep them in mind. There will be some time for questions during the panel session later, during the panel discussion later in the session. The next talk will be on an application of quantum technologies. It's on superconducting photon detectors from quantum information processing to metrology. It will be given by Professor Lixing. He's senior researcher with the Shanghai Institute of Microsystem and Information Technology of the Chinese Academy of Sciences. His research is about superconducting strip photon detectors, SSPDs, and their applications. He has produced SSPDs with record detection efficiency, which have been widely applied in quantum information processing. In 2016, he founded the photon technology company and commercialized SSPDs. In 2023, he was honored the ESA's Award for Excellence in Applied Superconductivity, and in 2024, the IEEE CSC Carl Rossner Entrepreneurship Award. As the project leader, he published the first international standard for SSPDs in 2022. Please. This is to the next slide. No, this is to the next slide. This is to go back. This is not. This. Good. Thank you. The big green.
Okay, so it's my great pleasure, and I have this honor to give a presentation here. So the previous talk, so Barbara already told us an overview about the quantum and the metrology. So now I'm trying to narrow the topic down to the photon. So to be frankly, I think I'm not the guy working on either the quantum or the metrology. Actually, I'm some kind of in between. So it's kind of superposition state. So the topic of my talk is superconducting photon detector from the quantum information processing to the metrology. So this kind of detector has some keywords on the name. So sometimes it's called superconducting nanowire single photon detector or the superconducting nanostrip or strip photon detector. But in the international standard, it's called SSPD, superconducting strip photon detectors. Okay, so this is the outline of my talk. So first, I will give you some background about this kind of detector. So today we are talking about the typical wavelength of this kind of photon is about the visible wavelength or the near-infrared wavelength. More specifically, we are talking about the near-infrared wavelength. It's 1550 nanometers, because we know this wavelength is a key wavelength for the telecommunication. It's a very important wavelength. And if we're talking about the energy of this photon, so since it's a very small value, so the energy is about, So energy is about 0.8 electron volts, and also in joule it's about 1.3 times 10 to minus 19 joule, or in dBm it's about minus 169. So it's a very small value. So for the typical lamp, like 10 watts, so every second we will have 10 to 20 photons per second. For a single photon detector, we are trying to catch all the photons, but it's not possible, but we are trying to do that. Okay, so previously there are already a lot of technologies about, for example, the PMT. So it's invented since 1950s. So it's already a commercial one. So it's based on the external photoelectric effect. So another one is called avalanche photodiode. So it was invented in 1965, and it's based on the internal photoelectric effect. So both these detectors worked quite well, but when we are talking about quantum technology, it's not good enough. Then we have this kind of new detector, but actually it's not new. So it's since 2001, about 25 years old. So it's called the superconducting strip photon detector, SSPD. So it's invented by the Russian professor Goldstein. So the mechanism of this kind of detector is a Cooper pair breaking effect. So this slide shows how this detector works. So it's I think it's kind of simple physics. So when we talk about superconductivity, it's a material, when we cool down to a certain temperature, the electrons in the material can couple. The two electrons can couple together into a Cooper pair. This Cooper pair have some kind of certain energy. Sometimes we call it superconducting gap. This energy is typically about a few milli electron volts, MeV. If we compare this Cooper pair energy to the photon energy, the photon energy, typical photon energy is about 1 electron volt, which means that 1 electron may break hundreds to thousands of these Cooper pairs. So for a superconducting material, it can switch to non-superconducting state or resist state based on the absorption of a single photon. So if we want to make this kind of transition effect to very clear or easy to observe, what we need to do is to make a superconducting film very thin. Then we narrow pattern it into a nanowire structure. The typical width is about 100 nanometers. So the shape will be like this one. It's a two-terminal device. It's folded into a meander structure. And this structure is good for couple the fiber. So that's it. So when we give this kind of detector a give it a bias current, the bias current is very close to critical current, but slightly smaller than the critical current. Then it's very sensitive. So as I mentioned, when a photon is absorbed, it will cause some local transition, local resistive state. Then the resistive state will grow. Then we will have a resistive barrier across the whole nanowire. What we can see is that when a photon is absorbed, we will see a voltage voltage pulse here. So it's very straightforward. So when a photon comes, we give you a voltage pulse. That's it, very simple. So if we compare the SSPD with some other technology like avalanche photodiode or PMT, photomultiplier tube, so the typical parameters like detecting efficiency, dark count rate, counting rate, or timing jitter, almost all of these parameters are much better than the traditional, the non-superconducting detectors. But the one point is that I have to mention is that it's the working temperature. It has to be cool to be very low temperature, so typical temperature is about 2 Kelvin. But fortunately, now we already have many commercial available cryo coolers which can support such a low temperature. Okay, so I'll talk something about the detector with a very high performance. So as I mentioned, this detector has to be operated at 2 Kelvin, so then we need a cryo cooler. So the cryo cooler is not a big issue now. So for example, I show you here. So this is just a cryo cooler. We have a compressor with this size and the cryostat with this size. Then if we package it, it can be in a rack with a height of about 1 meter. So it can be even smaller now. So this cryo cooler is, we can think it's just a refrigerator at home. The difference is that the compressor is slightly large, and also the cryostat or the container is slightly smaller. That's it. But the temperature is much lower. So, sorry, I think I cannot operate the animation here. So anyway, so this one is actually, that should be an animation of this cryostat. So it can contain many detectors. For example, I think now what we can, at most we can contain about like 100 detectors in one cryostat. So it has like many connectors for the fibers and also for the electric signals. So it has 3 shielding layers inside the innermost one. So it has a temperature about 2 Kelvin. Then we put all the detectors inside. If we can send the photons in, then we can have some voltage signals out. So that's it. So we are talking about 2 key parameters of this single photon detector. The first parameter is about the efficiency, detecting efficiency. So the detection efficiency is a product of optical coupling, absorptions, and intrinsic detection efficiency. So in principle, if we can make all these 3 parameters as high as possible, like unity, 1, then we can have the ideal detector. Of course, it's not possible, but what we can do is try to make all these 3 parameters as high as possible. But unfortunately, we noticed that. So these at least 2 parameters like absorption and intrinsic detection efficiency, that's not like independent value. It's like entangled together. They are both related to the thickness and the line width of the film. So which makes the challenge to how to optimize all these parameters. So I can show you some simple curve here. So if we use the thickness of the film as a parameter, with increase the thickness, we will see the decrease of the intrinsic efficiency, but at the same time, we have the increase of the absorption efficiency. If we reduce the thickness, we can see the higher intrinsic detection efficiency, however, with the lower absorptions. So that's a problem that we encountered. If we have the product, so the product will be less than unity. So what we need to do is try to either make this red curve to the right side or make this blue curve to the left side. Then we have 2 methods. One method is to use the ion radiation to push this red curve to the right side, or use this kind of, we call it a twin layer structure or sandwich film structure to make this blue line to the left side. So with the helium ion radiation, we can actually tune the superconductivity, actually to reduce the reduce the transition TC or reduce the gap energy of the superconducting material slightly. In this way, we can increase the intrinsic efficiency without any change of the absorptions. So with this method, we can have the detector with the efficiency as high as 97.5%. For another method, so we can replace the single layer film with this twin layer film with a sandwich structure. in this way, the intrinsic efficiency can keep the as high as possible. At the same time, we can improve the absorptions. In this way, we can make the detector with the highest efficiency with a value of 98%. Also, this is the best value we can have now. So also, we have some other colleagues, for example, the Wynand group at NIST, they also make this kind of detector, but with different material. So they use the molybdenum silicide. So they can have the efficiency of 98%. And also the group from TU Delft, but they have the value seems higher, but it's at a different wavelength. It's at 1310. And also, you will see here, the uncertainty is kind of high. Okay, so those slides shows that we already make the detector with efficiency very close to unit. But for a detector, we need it has a high signal-noise ratio. So we should reduce the noise. So if we check the noise behavior here, so this is like the holy dots here. So we see it has two parts. So this part is, we call it intrinsic dark count rate or intrinsic noise. So it's relative to the vortex mechanism of this detector. However, if we reduce the bias current, so this part can be neglectable. So now what we have is we call it background dark count rate. So we need to understand the contribution of this part. Actually, I mentioned this is a single photon detector, which means that for all the photons, even the thermal radiation or the black body radiation, we can detect it. So for the fiber coupled detector, so for the fiber, even if there is no signal in, the fiber itself has some finite temperature. So the fiber itself will contribute to the thermal noise or black body radiation. So what we have here, the background noise is contributed by the fiber itself. So if we need a practical detector, definitely we will have this kind of noise. So what we need to do is try to make this curve to the right side or to suppress the background noise. So this slide, this is more technical one, so I want to tell you that for the intrinsic noise or the intrinsic dark count rate, actually it's contributed by only the single defect or the worst constriction on this kind of nanowire. That will contribute most of the noise of this detector. So what we can do is try to find where is the narrowest part or where is the constriction on the detector. For example, in this, so in this meandered area, in this bending area, which contributed to most of the noise, then if we make this part of the film thicker, we can reduce the noise. We can make this kind of line to the right side. And more practically, what we need to do is to make a bandpass filter to filter most of the thermal noise. But the trick here is that this filter should be a cryogenic one, so we need it to operate at 2 Kelvin. So we can make this kind of bandpass filter either on the tip of the fiber, or we can put this kind of cryogenic bandpass filter on the detector directly. So in this way, we can make a detector with a high signal-noise ratio. For example, here we show the noise is about less than 1 count per second, and also the efficiency is about 90%. And for some specific applications, this is application for QKT, we need the detector with ultra-low noise. Then what we can do is to make this kind of more powerful bandpass filter. Then with this one, we have the noise, it's about 0.005 counts per second. At the same time, we can keep the efficiency over 50%. So another issue I want to mention is that, we talk about a single photon detector, but for this kind of traditional one, so it can detect single photons. However, if 2 photons or more photons comes at the same time, we cannot distinguish them. So then, for some applications, we need a detector with a photon number resolvability. So what we can do is to make this nanowire into different parts. For example, this one, we split this nanowire, a single nanowire, into 32 parts. And then for each part, it has a resistor in parallel. In this way, the pulse amplitude will be sensitive to the number of the photons. For example, for this one, so it can have efficiency as high as 98%, but it also has a low noise. But the important parameter is that it has a high photon number resolvability, as high as 32. Also, it has a high fidelity. So also we can make some other detector if we can make the wire wider. So for example, this is a microstrip. Also, if we can increase the kinetic inductance of this detector, in this way we can tune the slope of the rising edge, which is sensitive to the number of photons. In this way, we can also have this kind of a detector with a photon number resolvability up to 10. All right, so as I mentioned, so this kind of detector is very important. So to the quantum information processing, actually, it's because of the strong requirement from this society, we are able to make the better detector. So if we're talking about quantum information, it includes the quantum communication, quantum computation, also quantum metrology. So for the quantum computation, it's easy to understand. Single photon detector is important. For the quantum computation, now there are many different physical platforms. Of course, for optical quantum computation, it needs single photon detectors. And indeed, for many other physical qubits, they also need the optical single photon detector because, like, for example, for even the ion trap or for the neutral atoms, sometimes they need to change the signal to the optical wavelengths. In this way, single photon detector is also necessary. Of course, for the quantum metrology, it's very important. So I give you some more details. So for the QKD, so the quantum key distribution, so this image shows a typical protocol. It's called BB884. So in this protocol, they need at least 4 single photon detectors. Also, they need this detector with high speed, with high efficiency, and also the low noise, low dark count rate. For the quantum computation, so it needs many single photon detectors. At the same time, the efficiency of the detector should be as high as possible. So in the past 20 years, so the many scientists in the quantum society, they use the superconducting single photon detector to make the quantum communication better and better. I just show you the latest result. Actually, it's not the new one, but it's still the best result now. So for the QKD, for the distance, the longest distance recorded is already over 1,000 kilometers with a protocol called twin field QKD. For this result, it uses SSPD with ultra low noise. For another record, is about the highest the secure key rate. So now the best value is 110 megabps in 10 kilometer fiber. For this result, they use the detector with a very high speed. Also, the SSPD contributed a lot to the optical quantum computation. The milestone happened actually in 2020. It's called the 𝐁𝐈𝐏𝐿. So that's the first optical quantum computer which demonstrated the quantum advantage using the 76 qubits, optical qubits. And now the latest result is already over 250 qubits. I want to mention is that in this results, they use a detector. Now they use a detector is about over 100 single photon SSPDs. So because they needed cryogenics, so actually they use a special room to have the 10 cryocoolers, each cryocooler about 10 detectors inside. So actually this is a very huge system. Okay, I also want to mention is that also this kind of technology can bring us some business. So in the world now, it's about 7 startup companies working on these superconducting single photon detectors. We have the Photech in Shanghai. Also in Europe, we have the single quantum, and we have ID quantity. We have Pixel Photonics. In Russia, we have Scantel. Also in US, we have the Photon Spot and Quantum Optos. So this is as a scientific instrument, I think it's a very nice niche market. In 2022, we have about 240 sets installed, and the whole sales is about $40 million in the world. But unfortunately, I cannot have new data because now the quantum is more sensitive, right? So all the information we cannot get. So the quantum is really sensitive. Okay, so the last part is about the single photon detector, SSPD, and metrology. So I think what I will show you is not how good the result is, but is how many problems there are about the metrology of this kind of detector. So this one everybody knows here that we claim that we have in the SI we have the 7 base units in 2019. So it's like quantum related. But if we check the uncertainty, there's a huge difference for all these 7 base units. Of course, we have the very good one, like the seconds. So it has uncertainty is up to 10 to minus 16. However, so we also claim the candela is also quantum related, but the uncertainty is only 10 to minus 3. So it's a huge difference. So, but unfortunately, I'm handling with this kind of photon technology, which has the worst uncertainty at the moment. Sorry, this data may not be precisely correct because I'm not working on the metrology. I just got it from the DeepSeek. So the definition about this is a definition from about the candela or the luminous intensity. So there's some very precise description about the candela, but I will not read it. What I want to mention is that one candela has about like 4 times 10 to 15 photons with a wavelength. Actually, this is a green light. It's 555 nanometers per second within a unit solid angle. So it's very, to me, I think it's a lot of challenge try to make a better metrology for this one, even from the name of it, right? It's named after candle. So how unstable that could be. So if we want to have better optical metrology, so we need the better single photon source, the deterministic single photon source. Also, we need ideal single photon detector, but we don't have it at the moment. For the single photon source, what we have now is usually we use attenuated pulsed laser. And for the deterministic one, theoretically, quantum dot is a very good one. But we have a lot of problem about the noise. Also, the coupling is a critical issue for it. And if we're talking about the single photon detectors, we already have this SSPD, also the transition edge sensor, another superconducting detector is also a very good one. But we always have the problems on the noise and efficiency. So if we need a better optical metrology, we need a good single photon source and a good detector, but we don't have it at the moment. There's still a lot of work we need to do. But if we want to work on this kind of source or detector, we need a good metrology. Now that's the current state. So this is a paper from NIST by the St. Louis group. So this is how they try to characterize the single photon detector. We need a lot of things. We need a good laser, polarization controller, attenuator, optical switch, and a power meter. But we have a lot of problem with the uncertainty of this system. But if we have all these parameters totally, so what the error budget or the uncertainty of the efficiency we can characterize for this kind of detector is 0.47%. So that's the best result we can have now. So that's when we reach the 98% with this relative uncertainty. So this is the result from our group. It's about 1%. And this is the result from the TU Delft. It's about 2%. So we are now talking about a detector with an efficiency of 98%. If we are able to make a detector with a better efficiency, like 99% or 99.9%, how we can handle with this kind of uncertainty? That's a problem. So we need a better metrology for the candela. So that is essential to the photon technology or the optical quantum technology. So this is my last slide. So I'd like to summarize here. So the SSPD is one of the best practical photon detectors. So the quantum information processing and also this SSPDs need definitely, we need the better optical metrology. We need the better candela to characterize it. But on the other hand, I believe the next generation of candela may benefit from the better single photon detector. So, however, which comes first? That's our problem. But anyway, I think we are working on it. So that's it. Thank you.
Lixing, thank you very much for this fascinating talk about an advanced application of quantum technologies and the needs from the side of metrology. I think there's still a lot of work to be done. Again, if there are any questions, please keep them in mind for the panel discussion where there will be some time for a few questions. Now, this brings us now to the second part of this session, which will consist of a panel discussion between experts on quantum technologies, on quantum metrology. The discussion will be moderated by Professor Jan Theodor Jansen from the National Physical Laboratory from the UK. Jan Theodor Jansen, much better known as JT to most of us, of course, is the chief scientist at the National Physical Laboratory and a member of its executive team. He's distinguished for the application of quantum technologies and an NPL fellow in quantum electrical metrology. His research involves a wide range of topics in solid-state physics applied to metrology applications, such as single electron transport, Josephson effect, and quantum Hall effect. JT is a fellow of the Royal Academy of Engineering and a visiting professor of the University of Lancaster in the UK. He's a member of the CIPM and the president of the Consultative Committee for Ionizing Radiation. Please. You don't need that.
No, we don't need that. Otherwise, it's this. No. Thank you, Michael, for this kind introduction, and welcome to this first discussion session of the day. So we had two great talks about metrology in the quantum era, and yesterday we had a brilliant talk by Bill Phillips, who talked to us about the history of how we went from artifacts to fundamental constants, and that is really an enormous paradigm shift for the world of metrology, because of course the artifacts were held by the metrology labs. They were the custodians of these standards, very carefully looked after, and now of course we've transferred to fundamental constants, and the fundamental constants belong to everybody. I can go in my shed and realize a quantum unit tomorrow and disseminate that. So what does this mean for the world of metrology? How do we need to adapt to these changes in terms of how we disseminate our standards? And also, as we heard from Lixing, these fantastic applications which are being developed on the back of quantum technology, which can change the world of metrology and have lots of industry applications. And for all of that, of course, the metrology labs play a role. So I think we want to explore this topic in this session with four panel members. So we've got Barbara and Lixing, and then further on we'll be joined by Dr. Yifeng Qiu and Dr. Nicholas Spellman. I'll first read out the biographies of Yifeng and Nicholas, and then I'll invite everybody to come up onto the stage. So Dr. Yifeng Qiu is the Vice Director of the National Institute of Metrology, NIM, in China. He joined NIM in 2009 after a 3-year stint as a guest researcher at NIST. His research interests focus on electrical quantum metrology and its applications, especially on the development of portable quantum standards. His research on electronic measurements of the Boltzmann constant contributed to the redefinition of the SI unit for temperature Kelvin, which received the National Science and Technology Progress Award. He was elected as a member of the CIPM in 2024. He is a member of the National Technical Committee on Quantum Computing and Metrology of Standardization Administration of China. So, Dr. Yifeng Qiu. And then we'll be joined by Dr. Nicholas Spellman, heads the Quantum Technology Competence Center at PTB in Germany. Following several positions in quantum optics research, Dr. Spellman joined PTB in 2017. His work now focuses on transferring quantum technologies into applications, as well as developing metrology for emerging quantum technology industry. Dr. Spetman also serves as the co-chair of the Joint Technical Committee 22 Quantum Technology of the European Standardization Organization CEN-CENILAC, and as a convener of the Strategy Advisory Group of the Joint Technical Committee 22. Additionally, he's the co-chair of the Technical Committee 25, Quantum Measurements and Quantum Information of 𝐒𝐞𝐲. Dr. Nicholas Spetman. So if I can ask you all to join me up on the podium, please.
So maybe, Yifeng, we'll start with you because the other two speakers have been exhausted. So we start with the role of NMIs in this world of distributed quantum standards. So how do you see that role developing?
The role of NMIs in the area of quantum metrology, in the quantum era. Indeed, I have two examples for this question. The first is about time and frequency. As we all know that the definition of the second, based on quantum leaps, had been realized in 1967. And after about 17 years development, we now have widely distributed system clock every wire. But however, we still rely on the close collaboration between NMIs under the framework of international atomic time led by BIPM to reach the top-level consistency, the top-level, let me see, the top-level consistency, yeah, of time and frequency. And the second example is about the unit of mass, the kilogram. It was defined based on the Planck constant in 2019. And after that, indeed, to realize the definition, the metrology community developed, you know, the cable balance and silicon sphere to determine the Planck constant, and after the redefinition to realize the quantity value of kilogram. But as we know that the realized value by these two different approaches are indeed inconsistent with each other, with their claimed highest, the lowest uncertainty. So we have to give a consensus value through comparisons for the community as the realization of the kilogram. So from these two examples, you can see that both BIPM and NMIs, they still play very essential role in the quantum metrology area of both time and frequency and also mass. And indeed, similarly, after the redefinition of the all of the base units of the SI, we can realize them, all of the base units, or some other derived units by different quantum techniques. However, I think it does not mean that those realization by everyone and anywhere, anytime, is of no systematic error or is absolutely immune from the environmental fluctuations. So for this situation, I think in future, NMIs will still play very important role because that for both the realization of the already developed quantum standards or some new quantum standards, NMIs are responsible for validate those new systems. Also, NMIs are responsible for comparisons, international comparisons to realize the mutual recognition, and also NMIs are responsible for organized domestic comparisons to ensure that those distributed quantum standards are really of the so-called zero chain traceability. So in conclusion, I think NMIs will maintain their role in both realization and dissemination of the quantitative value, and also they will play a critical role in manage and organizing the real traceability, comparison, and some other things for the to ensure the traceability, the consistency of the distributed quantum standards. That's it. Thank you.
Thank you. Thank you, Yifeng. Nicholas, what was your view on the role of the NMIs?
Is this on? Yes. Yeah, well, first of all, I would agree to what you say, that this comparison, measurement, and understanding how well a intrinsic quantum standard works out in the field is a very important point. That still, for this, I guess we still need Metrology Institute's role. And I would add to this that this is also where the neutral position of a metrology comes in, of a Metrology Institute comes in, because this is something that maybe shouldn't be done by individual industry partners, but rather by institutes that do also international comparisons, ideally also by complementary technologies. That's also, I think, a very important point. I have two more things to add. I think one would be, we heard yesterday a bit about the role of metrology and making it known that it plays a role. And maybe now that there's a big chance to get intrinsic standards out in the field in, factories, apparatuses of some kind, communication devices, maybe it's even more important to explain why metrology is important and why traceability is important, if it is important. It's maybe not always the case, but I have the feeling this is even more important now. And my last and next point would be, I love the talk by Bill Phillips yesterday, and we now got rid of the scandalous artifacts. I think this is a great chance to push this technology that we have in NMIs a lot out into the field. And I think this is also maybe a role where NMIs have more to do to actually get the technology out of the pristine laboratories into application. And this is also something we cannot do alone, or maybe not even at all, but together with industry partners. And I think this is a great role and maybe the first step to a new development.
Yeah, thank you, Nicholas. So Barbara, in North America, of course, there are already quite a few companies who have got their own quantum standards, and how do they interact with NIST, and how do they make sure they got the right answer?
Yeah, so thank you for that question. I think that in the example I gave, that Honeywell picked up our public domain Nobel Prize winning research, built a whole company around it, you might have thought, okay, maybe NIST is done here, right? Because we don't compete with industry, and right, we need to make sure that we're not duplicating work, and they, of course, are throwing a lot more resources at it than we can, but actually that's proved not at all to be the case. They still come to us for cooperative research. They look to us for additional innovation, and they also look to us to make sure that we can produce the measurements. Another great example is a long-running collaboration we have with Xanadu, a Canadian company, where they have, a photonic quantum computing chip. So they're doing all the circuitry, but they look to us for our detectors. And then the combination of the two is a really important system in that collaboration, even though, again, this is a well-funded company that's, on a mission. They still look to us as a Metrology Institute to provide our expertise, but also our metrology know-how. And I think that also when we talk about standards going out into the field, right, who else but a metrology institute is going to know all the nuance it takes to trust those devices while they're out there? We're going to be the ones biting our nails and staying up at night, right? Because it's going to be it's a hard problem.
Yeah, because of course, even though the quantum standards are related to fundamental constants, you can still get the wrong answer, as we all know from experience. Lixing, last on this topic to you. I think it's on. It's on.
Okay, so if I count me as a user from the quantum society, I think we need more from the metrology side. And actually, to me, as a user, I think the quantum, the metrology is kind of far away from most of our applications. So as a user, we need like more practical, like metrology technology. But at the moment, I think it's not easy to use in most of the cases. That's one feeling from as a user. So on the other hand, I believe, as Barbara mentioned in the talk, so I believe there are a lot of new science and new technology, also including the quantum technology, can be used for the metrology. Actually, I believe that's the working of MMI. So they could have them like more quantum, even like the. For example, one point is like the quantum communication for the QKD, whether it's a way to distribute the data between the MMIs or some other ways. So if we're talking about the safety of the data or some other application, I believe the quantum information and also the AI should be included in the new metrology, new study of metrology or the new MMI rules. So the metrology should not be the traditional one. There should be some more new one or advanced one.
Yeah, you sort of start to introduce my second sort of question, which was around what sort of capability do the NMIs need to develop to support organizations outside the NMI community to use quantum standards like yourself. So maybe, Nicholas, do you want to go first on that one?
Yes, sure. Well, I think one thing that might be very useful is something that you could call test beds, so that you have something where people can come into your institute and work with you, because I don't think you can expect national metrology institutes to roll out this technology in its full width, but still you can give the right, quality infrastructure, base technology where people can test things and learn the technology and cooperate with us. So I think this would be one very important point, but also connected to your point, if things are not very usable, this is also something we cannot develop probably, but we can still obviously cooperate with partners. And I mean, at PTB, you mentioned a few examples. We also have examples of cooperation with academia and industry partners, for instance, for integrating optical table into what is now a transportable clock. We have other projects with pressure sensing based on a quantum technology, where companies are actually picking up this technology. And I think this takes time. I mean, it's not that easy, but test beds and open labs, I think, are a very important aspect, just to mention one.
Yeah, good point. Yifeng?
I totally agree with Nicholas about the test bed and open. I'd like to add some points that for further development of quantum standards and to support the non-NMI users, we need to develop some new metrology capability. The first, we need to extend the capabilities for smaller uncertainties and for some wider measurement range. Currently our quantum standards can realize the unit in a certain small range, but for application and indeed like the temperature measurement, we need to realize the thermodynamic temperature measurement under ultra low temperature or up to very high temperature. That's what we need to develop, the new capability. And also we need to develop some new measurements that links the fundamental constant with the measurable quantities to support some development of new quantum standards, except for the base unit like electric field, magnetic field, gravity, and force, and some others. And also, we need to develop capability to validate this new measurement standard, the quantum standard. Some other things I think that, again, comparisons to ensure the quantum standards, distributed quantum standards applied in industrial for the users can provide the real zero-chain traceability, something like that. Yeah, I think we need to develop those capabilities.
Mm-hmm. Thank you, Yifeng. Barbara, do you want to come in on this?
Sure, I always have a comment. So I think that any way that we can engage industry is really important in this field, especially as we're trying to boost a fledgling economy here. And there are so many ways that we can do that through public-private partnerships. So as I mentioned, NIST helped stand up the Quantum Economic Development Consortium. Many of our countries have something similar. Not all of them have been so closely tied to their NMI. If the National Quantum Initiative Act gets reauthorized in the US, it asks for NIST to stand up I think it's 1 to 5 new centers with more of a practical bent, the quantum engineering bent. And I'd say on NIST on a chip too, in this program, we have been, we're not exactly unique within NIST, but maybe unique in the way that we emphasize tech transfer. Because at NIST, we only develop technology to a mid-range TRL of 4 or a 5 at the most. And then, but this program can't be fully successful unless somebody out in the world sees a market opportunity and turns this innovation into a product. So we've been partnering, it sort of takes a village, right? We've been partnering with our Department of Defense, and the services have been helping us try to prove to industry that, gee, if you take this innovation that's only half-baked and you have to go finish it, look at all the ways that we need it. And here are, the number of products. If you hit these specs, this is, we'll buy, this many. They're not committing. It's a letter of interest, not a commitment. But so we're trying all sorts of innovative ways to sort of spur the market by proving to companies there's opportunities, by working hand in hand with them. And of course, standards is the last way that I could mention, right? We're trying to find new ways, and this just stood up a new standard center of excellence to try to help bring industry to the standards table, because it's an expensive proposition to commit a person to show up to meetings and you debate over commas for a year. But at the end of the day, those standards are really important. So we're trying to find ways to make that more palatable and facilitate that.
Yeah, you touch on an interesting topic around the standards development, and I think Lixing, of course, the industry and academia is moving very fast in the area of quantum technologies. There are new applications coming out on a weekly basis, and how should the world of metrology really respond to that? Are we fast enough and agile enough to support those developments?
Well, to me, the industry of this part, yeah, it runs very fast, but most of the time it's in the it's a niche market. If we're talking about I'm not sure whether now, if we're talking about the industry of quantum, it's a real industry or not. But to me, it's like the niche market as if we're talking about single photon detector, it's just a scientific instrument. So at the moment, we don't have strong metrology to support it. Mm-hmm. That's something just we claim it, but nobody knows. So whether it's a real or how confident it is. But the fortunate issue is that for the scientists, they don't care too much at the moment. So that's it.
So, Nicholas, you're on a number of standards committees, so you must be worrying about this topic a lot.
Well, okay, I would say yes, we are very active there as PTB, and the reason for me is that at this point of quantum technology, it's early in some sense for an industry, I agree with you, but then still it's important to set up the community to standardize and also to talk about terminology, how do we understand things, what is it we are talking about, and then also characterization of components, which obviously is very closely connected to metrology. Because in quantum technology, and I think this is a good thing, there's a lot of dynamic, let's say, and it's important to be able to understand what's behind it, let's say. So to have comparison not only in the sense of physical standards, but also to understand how well components actually perform and what the data sheet is, if needed, with traceable numbers in the end. And I think this is also an important part that metrology can play in, I think you called it managing the hype of quantum technology, to have some way for neutral comparison of technology and implementations of quantum technologies. And I think this is also where standardization will play a role, because this is what you would write in a standard. Okay, I have some device, I want to measure it. The measurement routines have to develop, but also the numbers, simply the characteristic I want to measure, and this could be a first characterization standard.
Yep. Barbara or Yifeng? Either of you who wants to?
Just to key on your point, both of your points about is it too early for standards, and there's a lot, this is an ongoing debate. We're probably going to be asking this question even after we have, tens of standards out in the market, but I just wanted to mention that at NIST, we've introduced this idea of standardization readiness levels to try to help fine-tune the timing of when is the right time to launch a standard, so that we, as I said, we sort of want them to be scientifically sound, and that's why we're launching NMIQ, but we also want them to fill industry gaps, and you don't want to get ahead on either of those curves, right? You want to know that there's a user community ready to adopt, a community of people ready to develop, and that we know enough about what we're doing to make a standard that doesn't need to be replaced immediately.
I think for the rapid development of quantum industry, both from the technical support from metrology and also the documentary standardization is not strong enough to support the rapid development of quantum industry. For example, that the quantum industry, like quantum communication and quantum computing, they do ask for some very strong support from metrology, like the quantum superconducting quantum computer. Some colleagues, they asked if we can provide them microwave power metrology with very, very high resolution, like to resolve the energy of one of the single microwave photon. So we don't have that kind of technique to provide the support. And also, of course, for the development of industry, we need to fill, like Barbara said, we need to fill the gap of standardization. Yeah.
Okay, well, before we go to questions of the audience, maybe one last sort of left field question. Do you think that in 150 years from now, do we still need metrology labs, or are the quantum standards so reliable and integrated that there is really no need for any traceability? Who wants to go first on that one?
Okay. Well, of course I want to say yes. I mean, but what we'll be doing in that phase, or, that's an open question. But I think it's a robust system, right? To have the folks that care about the integrity of the measurements that are being made, working hand in hand with the people making the devices that actually make those measurements. So exactly how that interplay works, it may look quite different than it looks today. I'd be very surprised if it doesn't, and who knows, maybe AI takes care of it all for us. But I know there's still a role there. So.
Nicholas?
Well, yeah, I would guess, and this is really just a guess, that there still will be metrology labs, and I could imagine that some part of it actually still looks like it does today, that you push the boundaries of realization of the units, because that's maybe something that early on is not interesting for someone else, and it's like a pioneering work. So I think this will be there, but then also comparisons and understanding how quantum standards out in the field will probably play a bigger role, as also you mentioned, comparisons between different realizations. I think this will be also a bigger part of it, but yeah, we'll see.
Mm-hmm. What do you think?
I think we will still need, yeah, definitely. As I said, that the quantum standard does not mean that the output is of no systematic error. Mm-hmm. Like the quantum voltage standard is well developed, but it was still affected by the electromagnetic interference. From that point, we do need some, like it's probably not calibration, but it's comparison, mm-hmm. To pursue the top level performance of the standard, and also for the miniaturized or even the on-chip quantum standard. It can realize the zero-G traceability with a certain uncertainty level, but for higher level accuracy, we do need metrology lab to play their role. Yeah.
Good. You think?
Okay, so as a guest on this floor, I have to say yes, right? So definitely, for the new technology comes, I think itself, for the quantum itself, it need a lot of new metrology. So today, now, most of the time, we are talking about some traditional quantum. We are not talking about some new parameters or something like, for example, for the entanglement. So what it is, how to do metrology with that one. So definitely there are many new metrology we should do with new technology like quantum. So that's it.
Thank you. So I think we got some a few more minutes now to have questions from the audience. I can't see. Ah, there we go. Of course.
So my first question, because I've got questions for everybody, but I wanted to ask Barbara a question. But first I had a comment. You mentioned that you talked to some physicists who said that maybe teleportation of people would be possible. And you know, a few years ago, a guy named Lawrence Krauss, a physicist, wrote a book called The Physics of Star Trek, and imagined all the ways in which the things that Star Trek did could actually happen, and talked about things like as weird as warp drive, how you might actually get a warp drive. But he absolutely refused teleportation. He thought that was just so far out that it was absolutely impossible at a time when we were teleporting, you know, photons, single photons and that sort of thing. But the actual question is, okay, we got these miniature grain of rice size atomic clocks. How long before we're going to have atomic clocks in our cell phones so they can be part of the satellite navigation system? Because I keep talking about this stuff, and people ask, you know, well, you know, I describe the, you know, satellite navigation, and I say, first imagine you have a clock in your GPS receiver, because it's a lot easier to explain how it might work. And then I say, sadly, we don't, so you need an extra satellite, but we're working on it. So when's it going to happen?
Well, could you just throw some money at John Kitching and tell him to hurry it up, will ya? So, of course, you know, I would get myself in trouble if I actually gave you a number, so I'm not going to do that. And afterwards, I'll tell you who thinks we can teleport people, because a NIST person, and you know them. But yeah, I mean, obviously, position, navigation, and timing, this is a real target application for miniaturized sensors and standards. And maybe the hope here, right, is that the closer we get to the application, the less precise we need to be, although clocks, I think, will still need to be fairly precise and to get them small. And, you know, I've been told also, don't hold my breath on optical clocks, you know, getting too small, right? So, but I think, you know, we'll get surprised by innovations in the future.
Any more questions from the audience? Oh, you go. Oh, there, Gert. Maybe shout.
Yeah, please wait for my...
Oh.
Yeah. My question is triggered by the presentation of Barbara and your final question, JT, which is on the future of NMIs in the quantum era. As a CCEM president in electrical measurements, we have quantum standards for 35 years. So for me, it's slightly easier to extrapolate to the future. So what I could imagine is that indeed quantum standards become like common in the industry world, but then there might be a role of more like, well, the keyword in your slide was verifying. So could you elaborate on that one? Could it be that indeed the case, that we would be more like verification bodies or whatever?
Right. I mean, I think this is still an open debate, right? How do we really manage this? And again, it comes back to the fact that, you know, we trust our standards. I mean, the way we do calibrations now, right, is you send us something, you hand it to the FedEx guy, you hope he doesn't drop it, you hope he doesn't lose it, comes to you, we take it into our pristine labs, we characterize the heck out of it. We can absolutely guarantee what we measured when we had it in our hands, right? But then we hand it back to the FedEx person who may drop it or lose it or jostle it, and then it gets back. I'm painting the most pessimistic picture here, right? But so we're hoping, right, that when we can actually disseminate the precision measurement to point of use, right, that we eliminate a lot of those risks along the way, but who knows what risks happen in that case, right? The dog chews on it. I mean, who knows, right? And so how are we really going to guarantee that it's continuing to perform? You can build in self-checks, but how do you guarantee the self-checks are working? So, yeah.
Yeah, and I think that's exactly the sort of the topic. The new task group on quantum for metrology is going to look at, and how to ensure that comparability over a wide range of quantum standards in and outside NMIs, and to try and provide guidance around that.
Yeah, maybe when it comes to clocks, it would be handy to have an atomic clock in your cell phone that you could just travel back and forth between, with your cell phone between clocks. That might be the future.
Great. Question over there?
Thank you. You were talking about interaction between technology and metrology, and this circle can lead to reduce uncertainty in the different realization of the different units. I wonder which is the limit of this reducing uncertainty. Is there a limit? Will we reach a time where uncertainty is really neglectable?
Very good question. Who wants to answer that one?
Why?
No, he doesn't. But well, I mean, this is kind of related to the question: will research end at some point, right? Because you can push boundaries. There's many questions we don't have answers to in physics. So I would say, as far as we know, it goes on. And I don't know, we'll see. Of course, there's, like in quantum physics, there is sizes of Planck constant, and you can derive different sizes from this. This gives you some kind of boundary. But I will stop talking here because this is becoming dangerous. But this is what I would, be thinking about.
Yeah, I think the only quantum standard which is really close to that regime is the clocks, because now clocks are at the part in 10 to the 20, and what does time mean at that sort of level? That's a complete different question. I think some of the other ones in electrical metrology, I mean, there's still plenty of room for improvement. As the technology improves, we can improve the accuracy. I don't think we're nowhere near the limit, and particularly there's still a long way to go with the candela. The question there at the back.
Yes, thank you. It was very interesting. The quantum physics is very complicated in general, and I would like to know how much metrologists need to know quantum to exploit them.
Good. Who wants to answer that? How much quantum does a metrologist need to know? Yifeng?
I think for metrologists, we are not working on fundamental science. So our task is not to resolve the fundamental question about quantum mechanics, but we do need to know the basic principle of quantum, and our main task is to develop quantum technology to apply those quantum principles in our metrology applications. That's what I can answer. Yeah.
Maybe I'll just add on that this makes me think about DFM, the NMI in Denmark. They have less than 50 people total, and I think half of their staff are quantum physicists, PhDs. So I think they'd say a lot. Yeah.
Yeah, and I think it's the task of us as metrology labs to make the quantum standard so robust and at a higher TRL level that you don't really need to know how it works. I mean, I don't know how a digital voltmeter works inside anymore, but we use it every day because you can just rely on it to work. And I think it's the challenge to bring quantum standards to that sort of level of operability that you don't really need to know how the inside works at some stage. I don't know how my car works, but I rely on it. Oh, there's plenty of questions now.
Oh boy. Sorry. So my ultimate question is, what are you doing for education? And let me explain the background of that. So I spend a lot of time with people talking about, well, what if we get the most exquisite, perfect clock? And I say, it doesn't matter. You can have the most exquisite clock, but it has no organic knowledge of the phase of frequency and time unless you set it to UTC. So we are here to push as the BIPM and to work on the dissemination or the synchronization of that time, because people get caught up in like, oh, I'll build that better clock. But unless you set it to UTC. So what is, as NMIs, are you doing to help further educate the people so they understand, yes, there's a drive to build a better clock, but we need to have robust disseminations who have calibration and traceability, because that's what has the interoperability, commerce, and everything else that we talk about.
Nicholas?
Thanks for the question. Very interesting. I can speak for PTB. We do have several programs in Germany where we have funding in research and technology transfer also with companies. And what we try to set up there is metrology that's needed for future applications, for instance, for QKD, as we heard about. And included in those projects is most of the time also, well, education or knowledge transfer of what metrology actually is and where you need traceability, because you also don't need it every time, right? And that's also an important message. So we have it included in projects, and we also have a few dedicated people working on that. And from my experience in our projects, that's something we have to do repeatedly, let's say. So that would be my answer. Yes, we do it in projects, and I think it's an important thing to do.
And I'd say at NIST too, we run multiple short courses. And Catrice Lippe is here from our Office of Weights and Measures. They have a very robust training program. So we're very aware of trying to take our knowledge. So we're not just getting our standards out of the lab, but we're getting our metrologists out of the lab too, so that they can help educate folks.
Thank you, Barbara. I think we've sort of, oh, is there still one last question over there?
So, I have the microphone, so I use it.
Possession is 9/10 of the law.
And Davide Calonico from IRIM. Just to add on the debate of metrology for quantum, and we should also pay attention of a sort of over expectations from the industry, because maybe they can start to ask, we can trust you, you can certificate, you can do standardization, and so please tell me that my QKD device is secured and is not attackable. And this is something that could be a bit embarrassing when the reality comes in confrontation to over-expectation. May you comment on that?
Mm. Who wants to comment on that? Barbara?
Yeah, you know, it's funny, at NIST we have like a random number beacon, and we've worked a lot on, you know, quantum randomness, and boy, you can get people to be really aggressive and hostile when you ask them at NIST if they can certify other devices as certifiably random, and they're very careful to say we can certify that the way we produce randomness is, you know, that's solid, but you know, they don't want to be in that business of saying this product, you know, checks that box. It's a very hard question. I think that we're going to struggle with this, especially because under the hood, right, we're expecting quantum magic to happen, right? And, you know, users aren't going to know, so they are going to want help.
Thank you, Barbara.